Hey, this is chapter 4.3, Modeling Linear Trends. We saw in our previous class that we can use a scatter plot to determine whether a trend exists between two quantitative variables, and then we can measure the strength of the association between these two variables. Today we'll take a look at how to find a linear model that best describes the trend seen in a scatter plot. We will also learn how to use this linear model to make predictions. And so the model that we will be using consists of a linear equation and a set of conditions that describe when the model is appropriate to use. This model is a good fit of the data, meaning it gives an accurate description of the data, then any understanding we gain about the model accurately applies to our understanding of the real world. And this linear equation gives us a regression line that summarizes the relationship between two variables, but only in a specific setting. One of the variables helps explain or predict the other. That is, regression describes a relationship between an independent explanatory variable and a dependent or response variable. In other words, a regression line is a straight line that describes how a response variable y changes as an explanatory variable x changes. We often use a regression line to predict the value of y for a given value of x. The table below contains many terms used for the x and y variables in regression. And so first off, when we say x and y variables, we're talking about the x variable that goes on the x-axis. Y variable is the one that goes on the y-axis. Something you might be more used to from algebra. Remember, the x variable can also be called the predictor variable. This is the one that's going to be doing the predicting. It's also called the explanatory variable because it helps explain what you're seeing in your y variable, your response variable. And then again, something maybe more familiar to you from algebra, but it's also called the independent variable. On the other side, the y variable is the predicted variable. It's the one that gets predicted. It's your response variable. It changes in response to x. Or it can be called the dependent variable. So it depends on the value that you plug in for x when you're making your predictions. All right, so for instance, and just an example here, number 4, the following scatter plot shows a moderately strong linear trend between the distance to a destination and the cost of airfare to that destination. And so notice distance is on the horizontal axis, it's your x variable, and this is measured in miles. And airfare on your vertical axis is your response variable, and this is measured in dollars. So notice that the airfare tends to cost more for the destinations that are further away. Right, the line drawn in is the regression line and can be used to predict the airfare for flying to a particular destination. Again, that's your response variable, based on the distance to the destination, your explanatory variable. So a couple other notes about this scatter plot. Keep in mind that each point comes from one observational unit. So in this case, 1 point gives you the information for one flight. So if we look more closely, it's going to give you the distance to that destination and the airfare for that flight. Also, again, this regression line that is included, remember, is a model for this data. It's a statistical model, again, for the data. Okay, so as an example of what we mean by model, keep in mind that what we're going to be doing with this, what our ultimate goal is we can use the line and the line's equation to predict the airfare for a distance of something else, maybe for a distance of, let's say, 500 miles. So if we go to our model, looks like this would be a good prediction for the airfare for a flight that's 500 miles away. And keep in mind that models aren't perfect, but it's going to be up to us, the statistician, to judge how well the model conforms to our data or to reality. And just a couple other notes about a model, or this regression model. Keep in mind that we're using it to summarize the variable collection of data, where you're going to use that with numbers. Typical value of y depends on the value of x. So again, what we plug into our regression model, what x value we plug in, is going to determine the y value that we get back out. And the next page, number 5, this regression line can also be referred to as the line of best fit, since it best fits the trend in the data. And there's also one more name for this regression line. It can be called the least squares regression line. And that's a name that we're going to learn a little bit more about in your group activities. We'll see why that name or why that name's appropriate. Okay, number 6, the regression line is the line y hat equal to a plus bx. And we do read this symbol as y hat. Think of it as a y with a hat on top of it. Right, that's in the equation of the regression line to emphasize that the line gives a predicted response, again, that y hat, for the x that you put in or for any x that you put in. Because of the scatter of points about the line, the predicted response will usually not be exactly the same as the actual or observed response y. So again, your predicted response y hat hopefully is close to the actual response value y, right? But they're not usually exactly the same. Right. Another note about this may look a little different to you, but it's very similar to what you saw in algebra when you dealt with the equation for a line, y equal to mx plus b. So there are a few differences. First major difference is they use different letters for slope and a different letter for the y-intercept. And they also rearrange the order of these two terms. So instead of putting the term with the x variable in it first and the y-intercept second, notice that the term with the x variable is second, and the first term in that side of the equation is your y-intercept. And that's just to make it easier. For instance, if you were going to go on and study statistics in, let's say, a statistics 2 class, you would find that you can build these models with additional variables. You don't have to limit yourself to one explanatory variable. So this format of putting the y-intercept first makes that a little bit more convenient to do. Okay, so again, regression models, you'll find if you go on, are often built on more than one explanatory variable. All right, so if we return to our example, and this is the one with distance and airfare, and just a reminder, airfare was measured in dollars, distance was in miles. The equation of the regression line in our example is predicted airfare equals 83 plus 0.117 times the distance. So that's giving us the equation of this regression line right here. So I can write that a little bit differently. I can just say that airfare, and with the hat on top, so that hat replaces the word predicted. Predicted airfare is 83 plus 0.117 times, and those parentheses are for multiplication, times the distance. And so we're going to take a closer look at the slope and the y-intercept, because one of our major focuses with regression is how do we interpret these values? What is the model telling us? All right, so we're going to start with slope. All right, so the slope of a regression line is usually important for the interpretation of the data. The slope is the rate of change, or the amount of change in y hat when x increases by 1. So let me start off with a reminder here from your algebra days. And that was that slope is rise over run. So rise is in the vertical direction. Think of a hot air balloon rising. And run is in the horizontal direction, like if you go out for a run. So you might remember this formula from your algebra class, and that was y2 minus y1 over x2 minus x1. And that was built on the idea that you had the coordinates of 2 points on the line. So you had x1 comma y1, and you had the other point, x2, y2. Okay. We also have another way of describing this. We can think of it as the change in y, and we use delta or the triangle to say change. It's a change in y over the change in x. And this last one may help us a little bit more when it comes to interpreting these. All right, so first step, what is the slope in the above example? Which value, what number is our slope? Well, remember, slope is always the coefficient of your x variable. So that's going to be the 0.117 in the above equation. So remember that that is the coefficient of the x variable, or the explanatory variable. Again, coefficient's just the number you're multiplying the x variable by. Okay. And in terms of statisticians, we use the symbol B, or the letter B, to represent that. Right, so how do we interpret this? Let's take that last piece from above, change in y over change in x. That's just in fraction form, or you can think of it as a ratio. Let's put some numbers in. Here's our slope, so I'm going to bring this down. And in order to put this in a fraction, we could certainly think about place value and that the 7's in and do it that way, but we're going to do it a little bit more simple way. We're just going to put it over 1. And any number over 1 is itself. So I've got the same value there, but I now have it in a ratio or fraction form. And then to make interpretation easier, we've got to include some units. So keep in mind that our y variable, if we go back up here, was measured in dollars, and our x variable was measured in miles. Let's go down and include this here. So our y variable's on top, that was the one in dollars. X variable's in the bottom, that's the one measured in miles. Okay, so now we have a fraction that says $0.117 per 1 mile. Yes, I don't need the S there. All right, so two ways to interpret this. So I'm going to read through those two. I'm going to press pause. I'm going to write them down. And you can do the same. And so one way to say this is that the predicted price increases $0.117 for each additional mile. Or you could say that the price goes up or increases $0.117 for each additional mile on average. All right, so again, those two interpretations, notice that the first one has this word in it, predicted. And it's a reminder that this is from the model, so it's talking about how the predicted prices are changing. So the predicted price increases $0.117 for each additional mile. And again, it's not guaranteeing that the actual prices are going to go up that amount for each additional mile. And the second one handles it in a slightly different way to remind us that, again, it's for the model. So the price increases $0.117 for each additional mile on average. And so on average, it's going up that much, or the price is going up that much for each additional mile. In fact, you'll see later that the regression line is also called a line of means or a line of averages. Okay, so let's take a closer look at the y-intercept. So I've got the equation of the regression line in our example again. It's predicted airfare. It's equal to 83 plus 0.117 times the distance. We've got our scatter plot again. And just a reminder, airfare is measured in dollars. Distance is measured in miles. Right, so number 8, let's look at the intercept. So it says the intercept of a regression line is the value of y hat when x equals 0. Although we can use the value of the intercept to draw the line, it is statistically meaningful only when x can actually take values close to or equal to 0. So what is the y-intercept in this example? Notice here is where we have an x value of 0 or 0 miles. I go up. Here's the point on our model or our line that has that x coordinate. And if I go over to the vertical axis, it looks like it's above 75. If I look more closely to my equation, I can find that this must be at 83. So here's my y-intercept. It's at 0, 83. And so again, the y-intercept in this example, we use the symbol A or the letter A, is 83. And does it make sense given the context of this data? So keep in mind, this is the cost of the airfare, or the predicted cost of the airfare, when the distance to a destination is 0 miles. So this may not be practical in this situation, may not make sense, unless maybe it covers the flat fees associated with flying. But ultimately, you probably aren't going to pay for airfare if you're not going to go somewhere or not fly somewhere. And so I'm going to press pause, put that interpretation down or that statement down. All right, so just to read what I wrote down here, again, the y-intercept, that's the predicted price of airfare when the distance that you're flying to or your destination is 0 miles away. And whether it makes sense or not, probably not. It may not be practical in this situation. You could argue again that it might be flat fees associated with just buying the airfare, but ultimately you probably wouldn't pay for airfare if you're not flying somewhere. Right, so use this regression equation to predict the airfare for a destination that is 600 miles away. So we want to use the equation in this case. So remember that our equation was that the predicted airfare, and you can look at the top of your page to double check this, but your predicted airfare was equal to 83 plus 0.117 times the distance. All right, so since we're given a distance of 600 miles, that's going to be substituted in our equation in place of distance. So we get that airfare, with that little hat on top saying this is a prediction, it's equal to 83 plus 0.117 times 600. And I'll leave it to you to verify this. You should grab a calculator and double check. And double check your order of operations. Remember, you want to multiply before you add. But you should get a predicted airfare of $153.20. So remember, this is a predicted airfare. And so if we go back up to our scatter plot, and we were doing a distance of 600 miles. So what we did was we just found the coordinates of this point on the regression model. So we found that it is a distance of 600 miles and has an airfare, predicted airfare of $153.20. So notice if I use the graph itself, I get a slightly less accurate prediction because I don't have quite enough detail on the vertical axes or the horizontal axes for that matter to find it. If I had just limited myself to the graph, my prediction might have been a little under 150, maybe around 150. And the equation itself takes out the guesswork. So if you're asked to do a prediction and you have access to the equation, it's best to use the equation. All right, so our last question here on this page, how does your predicted value compare to the actual airfare of the destinations that are around 600 miles away? Let's go back up to our scatter plot and see. And remember that this here was our prediction. This was a y hat value for a distance of 600 miles. Also notice we do have 2 points in here that look like they have distances of around 600 miles. And they're both somewhat similar to our predicted value, or predicted airfare. We've got one that's a little bit higher, one that's a little bit lower. So I would say that our predicted airfare appears to be similar to the actual airfares for destinations that are 600 miles away. Doesn't look overly unusual. Okay, so we got a predicted airfare, and that was the $153.20. Appears to be somewhat similar, roughly similar, to the actual airfares for destinations that are around 600 miles away. Okay, so number 11, this is on the next page. This is assuming that the data used to find the regression line are representative of all airline flights, then our predictions should give us reasonable estimates of the airfare of future flights. Since the primary goal in regression is to use this equation to make predictions about future values, then the best regression model for our data should minimize the errors from our predictions. These errors are also called residuals, and they're calculated with the following formula. So residual is equal to y minus y hat. So keep in mind, this is another way of saying that your error is equal to your observed value. Remember, y is the observed value, the actual airfare, minus the predicted airfare. So you can also think of this as the actual, your error is equal to the actual airfare minus your predicted airfare. Some people call it a fitted airfare because it fits the model. Visually, we'll take a look at what a residual looks like. A residual is a vertical distance from an observed y value to the predicted y value. So we're back to our airfare model, or our model for airfare and distance. So again, dollars and miles here. Here's that regression line, or a regression model. And it's a model for our data. And if we take a closer look, we're going to start with this point down here. This is the actual airfare for a distance that's around 800 miles away. So this is a y value. Here, if we go straight up, we get what's called the fitted value, or your predicted value, or in this case, your predicted airfare. So that vertical distance between them, this distance right here, is your error or your residual. So we calculate that by taking y minus y hat. And notice in this case, that's going to give us a negative value. So we call this a negative residual in this case. And it turns out any of these points below your regression line are going to have negative residuals. And so again, in this case, let me change that just a little bit. I'm going to say that this is less than 0, which gives you a negative residual. All right, on the other side, we'll see why these are positive residuals. So let's take a look at this one as our example. So in that point I just colored in green is the actual airfare for a distance that looks like maybe around 1,200 miles away. This point here is your y hat. It's on our model. It's our predicted airfare for that distance. And this difference between them, or that vertical distance, is called your residual. And we calculate that by doing y minus y hat. And in this case, since y is taller or higher up on your graph, it's greater than your predicted value. So you get a difference that's greater than 0. And as a result, we call it a positive residual. And a good model is going to minimize these residuals. It's going to give us the smallest amount of error possible. So you're going to take a closer look at these residuals in today's group activity. All right, so our last thing here, number 12, so just a caution. Always check a scatter plot of your data for linearity before calculating the correlation and before doing regression. Otherwise, your results could be misleading. So again, the model you're creating is a linear model. We want to make sure it fits something that has linearity, or it's being used for a scatter plot that has linearity. Other thing to keep in mind is that it's a statistician's job, or statistician's job is not just to produce the correct numerical values for regression, but you also want to make sure that you're determining whether a linear regression is appropriate. And again, that's why you need to examine the scatter plot to verify the trend is linear. You also have to keep in mind that you want to make sure that you're interpreting the output from the regression analysis. And what's the slope? What's the y-intercept telling you? What about those predictions?